Stare at a wall of television static. Every pixel a random speck of nothing. Now watch. In 60 heartbeats, that static sharpens. A face appears, a coastline, a cathedral at sunset you have never seen before and no one ever photographed. That's the trick you're about to understand. You feed it chaos. It hands you a cathedral at sunset. It shouldn't work, and yet it does, reliably at industrial scale, 1,000,000 times a day. So the question you're here to answer is the obvious one. Why on earth does this work? Before the magic, the mundane. Every image you've ever seen is a grid of pixels. Every pixel is just 3 numbers, red, green, blue. A single full HD frame? 6 million numbers in a particular arrangement. Change the arrangement, and you change the picture. That's all a photograph is. Pure noise is the same thing. Grid, pixels, 3 numbers each. Only now the numbers are dice rolls from a bell curve, the familiar Gaussian, the shape your teacher drew on the blackboard. Every noise pixel, 1 independent roll. Nothing more sinister than that. Hold that picture in your head. Picture an impossibly large map. Every possible image is a single point on it. Cats over here, mountains over there. Static scattered like dust across the rest. Real photographs cluster into small, dense islands in an ocean of meaningless noise. Generation is the problem of steering a random point onto one of those islands. Start with a clean photograph. Now sprinkle on a whisper of that bell curve noise. Just a touch. Do it again and again. 1,000 times. Slowly, patiently, a coastline dissolves into snow. This is forward diffusion, and it's completely mechanical. No learning, no magic, just addition. The researchers pick a schedule. How much noise at step 1, how much at step 2, on through step 1,000. By the final step, every trace of the original has vanished. Cat, car, cathedral, all end up indistinguishable from pure Gaussian static. That symmetry is the key that unlocks everything. Here's the leap. If you could reverse that process, noise would turn back into an image. Nobody can invert 1,000 rounds of randomness analytically. The math is a brick wall, but you don't have to. You only need to undo one small step at a time. And that, a neural network can absolutely learn. Hand the network a noisy image and one number, the time step. It predicts exactly what noise got added at that step. Subtract the prediction. The image becomes a touch less noisy. Now do it again. 1,000 gentle nudges later, a picture walks out of the fog. The training recipe is almost embarrassing. Take a real photograph. Add a known amount of noise. Hand the network the noisy image and ask it to guess the noise you sprinkled in. Punish it when it's wrong. That one repetitive task, performed on billions of examples, teaches it the shape of every visual concept humans have ever photographed. The workhorse network is called a U-Net, named for its shape. It squeezes the noisy image down through a funnel of coarser and coarser layers, then expands it back out. Along the way, skip connections shuttle fine detail across the bottom. The result? A network that knows what the image is and exactly where every edge belongs. The shape is literally a U. The contracting path shrinks the image to a thumbnail of pure meaning. The expanding path inflates that meaning back into a pixel-perfect prediction. And the horizontal skip arrows are crucial. Without them, every freckle and eyelash drowns in the bottleneck. So far, the network paints whatever looks plausible. To make it obey a prompt, feed your text through a model called CLIP that turns language into a vector of numbers. At every denoising step, the U-Net peeks at that vector and lets the word steer its guesses. Classifier-free guidance cranks that influence up or down like a volume knob. Watch the words travel. Your sentence becomes a list of numbers. Those numbers flow sideways into every layer of the U-Net through a mechanism called cross-attention. Now each denoising step asks a sharper question. Not just what image is hiding in this noise, but what image consistent with the sentence is hiding in this noise? Denoising 1,000,000 pixels 1,000 times over is brutally expensive. Stable Diffusion's insight? Compress the image first with an autoencoder down into a tiny grid called the latent. Run the whole diffusion dance in that shrunken space, decode only at the very end. Suddenly, the cathedral fits on a laptop GPU. For a decade, GANs ruled image generation. Two neural networks locked in combat. Forger versus detective. Powerful, but notoriously temperamental. Diffusion replaces that duel with one patient regression. Every extra training step makes the model better, never worse. The outputs are more varied, and the math hands you knobs for quality versus diversity. Once the recipe worked, it went everywhere. Photorealism, indistinguishable from a camera. Illustration, in any style a human has ever invented. In painting, where the model denoises only the hole you cut in a photo. Then video, where the noise spans time as well as space. Then 3D, same patient trick, pointed at whatever modality you throw at it. None of this works without scale. The largest open models devoured more than 5 billion image-text pairs, over hundreds of thousands of GPU hours. That is the cost of learning the visual vocabulary of an entire civilization. Someone else already paid it. You repay nothing, one prompt at a time. Here's the sentence to carry with you. A diffusion model doesn't paint a picture onto a blank canvas. It sculpts. The image was always hiding inside the noise, waiting. If you only knew which grains to chisel away. Training is how the network learns that chisel. Next time a model hands you a cathedral at sunset, remember what it really is. 6 million random numbers. And a network that learned, one small step at a time, which grains of noise did not belong. That's all it is. That's everything it is.